Okay, maybe we can get started. Hello, everybody. Welcome to today's event on the networking channel. We will be having an event today called Network Programmability, The Road Ahead. And it's going to be organized as a panel led by three very qualified individuals. The organizer is Nate Foster, who's professor of computer science and associate dean for research at Cornell University. He's also platform architect at Intel. He's the recipient of numerous awards for his foundational contributions to the field of programmable networking. He has received the Sloan Research Fellowship, the National Science Foundation Career Award, the SIGCOMM Rising Star Award. We also have Nick McKeown, who's Senior Vice President and General Manager of the Network and Edge Group at Intel, professor of Stanford University. He's the creator of numerous companies that have had massive impact on the way we build computer networks. He's cited as the world's leading expert on router design by the British Computer Society, recipient of the Lifetime Achievement Award from ACM SIGCOMM. We also have Jennifer Rexford, who's provost of Princeton University, Gordon Y.S. Wu Professor in Engineering, served on the advisory council of the SCIES Directorate of the National Science Foundation, former chair of the ACM Special Interest Group of Data Communication, member of the National Academy of Sciences and the National Academy of Engineering, received the ACM SIGCOMM Award, ACM's Grace Murray Hopper Award. So before we get started, we also wanted to mention that the networking channel is not just one event, it's a series of talks that happen every 2 weeks. And 2 weeks from now, we're going to have a very interesting event on artificial intelligence for networking, which will also be structured as a panel led by Christophe Dio from Google, and including 3 world experts who will have many interesting insights on research in this space and the future of that topic. So with that, we can start the panel for today. One of our goals is to keep things informal to make it easy for you to all to join in and guide the conversation to your interests. So we want to strongly encourage you to feel free to interact with the panelists. You can use the Q&A feature in Zoom at the bottom of your screen. You can also enable closed captions if that is helpful for you to see what is being said transcribed in text on your screen. And now I'm going to turn things over to Nate, who will be taking things from here.
Great. Thanks so much, Matt, and thanks to Matt and Jim for organizing the networking channel. It's a really wonderful community initiative, and we're really happy to be here to talk about network programmability today. So one of the weird things about getting older is that time seems to go faster, and it's hard to believe that it's been 15 years, almost to the day, since the original OpenFlow paper was published in CCR, and about 10 years since the early design work on what became the P4 language started. And I think it goes without saying that the movement from sort of pre-SDN days, where the network was ossified and fixed function and really hard to change and control, to today, where we have top to bottom, end-to-end programmability, has truly been a revolution. So it's exciting, but we're also at an interesting moment in 2023. And so we thought we'd use this session to spend a little bit of time, contrary to the title, looking backwards and just kind of take stock of how far we've come and what are the lessons and successes that we've had, but especially to try to chart a path for the future. And of course, it's hard to predict the future, but nevertheless, we're going to do our best to try to offer some thoughts about where the field should go or where it might go. As Matt said, we want to keep this fairly informal and interactive. It's wonderful to see so many of you online. I think there's over 140 of you right now. Feel free to ask questions in the webinar chat. I will do my best to monitor the chat and elevate some questions to discuss publicly. We may not have time to get to every single question, but we'll do our very best. And Matt's going to provide a backup in case I get overwhelmed with trying to multitask as I'm doing that. All right. So I think Matt already introduced us, very kind bio. So maybe I'll just jump in with a question. So in this decade since the P4 language and in general, sort of the next phase of data plane programmability emerged, what do we think are the most interesting or compelling killer apps that have emerged? Jen, do you want to start?
Yeah, I think to me, network telemetry has been the first killer app, and it's for 2 reasons. It's important in its own right that for running the network, you need to know what's going on. But more importantly, it's also the first step towards taking any action in the network. I mean, knowing what's going on is sort of harder than knowing what to do about it. And once you know an attack is coming, the right thing to do is block it. Once you know there's congestion, the right thing to do is to route around it or rate limit. But actually detecting and diagnosing those security and performance problems has traditionally been really difficult. So I think it's a natural killer app and also a prerequisite to a variety of other killer apps. I think also it's just been really helpful. Programmability has been an eye-opener for trying out new functionality and being able to stress test whether a new idea works well in practice and whether it can work at line rate at high speed. Even if future switches aren't entirely programmable, having a litmus test for knowing something is implementable or not is a really important goal that's been achieved by these devices.
Yeah, I would echo strongly the what you said, Jen, that network telemetry and the ability to measure anything that the switch or router or any device in the network sees. I mean, if you cast our minds back to 10 years ago, for those of you that are old enough to remember, at the time, network telemetry meant gathering counters every few tens or hundreds of milliseconds from switches as to what it's seen in the last window. So if you're looking for a particular event or something that happened on any sort of packet level or even round trip time scale, you were just going to miss it. And so the ability to put that telemetry right into the switches and routers really changed the way we think about it. Now we kind of take it for granted that you can do it. Now it's worth asking the question as, why do you need programmability in order to have telemetry? Wasn't it something that was kind of obvious that you needed already? If you want to control something at scale, surely you need to observe and measure it. It wasn't that it was difficult to do. It was difficult to know how to do it and where to place what to measure and where to place the information in order to bring it out of the network. Because different networks work with different protocols and different header formats. And if you're designing a fixed function switching chip, you're going to be able to support all of the different modes and put measurement into all of the different locations. And it's kind of impractical to do that, particularly when you're starting out and you don't really know who wants what. If it's programmable, you can just leave it up to the equipment manufacturer or the owner and operator of the network to decide what they want to measure. And so it allowed to kind of bootstrap it. And so I think now we kind of take it for granted that we will continue to measure at that fine granularity in the future.
Yeah, I'll just add one point to that. I agree with that completely. And it's not just about granularity. It's also that new applications keep coming on the horizon. We wouldn't have known 10 years ago that we'd want to parse Zoom packets, for example, like, we're on Zoom right now. And so being sort of future proof for not only for applications in general, but particularly for telemetry means we have to be able to adapt when new header formats and new applications come along.
Yeah. Now, in terms of the killer commercial apps that have been deployed, the biggest ones that I've seen have been where big cloud service providers have needed to do a big upgrade. And so they're actually moving from one protocol to another, one format to another, or in the case, Alibaba talks about this publicly, of when they were moving their commercial website over onto their cloud infrastructure. And so they needed a lot of translation, and they needed to be able to do that at line rate just because of the sheer volume of traffic. So being able to put appliances that were programmed that would be there, modified, updated as they go and as they change the infrastructure, that's a sort of a pretty typical use case as well.
Yeah, I'll jump in with, so I'll have to say the first time I heard about P4, I was not involved with the initial design of P4. I kind of didn't get it, and I had to have my students come read the paper closely and start playing with some of the early software to kind of educate me about what it was about. And the reason I didn't get it was I didn't quite grasp how powerful it was to be able to just take some idea and build a credible high-speed implementation of it. So even the kind of rudimentary dumb things like, I think, VXLAN, for example, was an example that sort of intellectually motivated the need for data pipe programmability. That shift of control, of not having to wait years and go build community consensus and go wait for hardware just to do, just to have these few bytes in a packet do something different. I know this is kind of with the two of you, I'm speaking to the choir, but like, we should have that freedom, right? And it's intellectually very, very freeing to be able to just go do something, even if it's just something simple.
You probably heard me say this before, Nate, but I would say that if you what does a network do? A network takes packets from one place and it moves them somewhere else. And in between, some device looks at some bits in headers and then maybe twiddles some of them. I suppose it's our dirty little secret of networking that's really all networks do, right? Is that they take packets from one place to another and twiddle some bits on the way. If you can't control how those bits are twiddled and what bits you look at, then you're not really in control of the network. Somebody else is. And so I think it's a sort of a basic primitive that we want and need, particularly if we're to just sort of keep improving the network. And I think that it has, turning to the question that Mario asked, actually, I think it's quite relevant here in the chat about the heterogeneous strategies for telemetry, and also the difference between networks that are heterogeneous and homogeneous in the way that they're structured. The programmability is very relevant here, because if somebody has, take a big cloud service provider or a big communication service provider like an ISP, if they have a way in which they want their network to operate, they would like to think of it as homogeneous. They would like to think of it all working the same way. Underneath, it may be built out of different pieces of equipment. So if you hold a program that specifies the behavior that you want, that you can then compile down to operate on that network, whether it's in the kernel, the user space, the NICs, the switches, wherever it happens to be, you've actually now turned something which is heterogeneous into something that has a homogeneous behavior. And really, that's what you kind of want as an operator of a network.
Yeah, a couple points on that. I think that points to languages like P4 is more like an intermediate language for dealing with the device heterogeneity below, which I think is an important use case. Another early set of conversations that Nick and I heard about when P4 was just getting started was people who wanted their devices to do less. Right, they didn't want to necessarily take a fixed function device and have a certain amount of memory in the device for access control and a certain amount for Ethernet forwarding and a certain amount for IP. They wanted to say, well, I only want to do Ethernet, so I don't want to leave fallow all of these resources in the switch that were devoted for functionality I'm not even using. And I don't want to parse headers that I'm not using, because that might be a security vulnerability to have a lot of complex goop in my device that I actually don't even care about in the first place. So being able to functionality is really valuable too.
Yeah, that's a really good point. If you look at the fixed function switching chips that are used to build cloud data centers, last time I looked, they have about between 40 and 45 features. It's probably 42, right? But those features are the features that somebody has baked into the silicon. Now, the typical cloud service provider, in my experience, uses about 7 different protocols in the network. So it's like, why do you need 45 if they're only using 7? The problem is they all use a slightly different 7. And so if you're building that fixed function device, you've got to actually build the union of all of those different features. So the most common interest that I've seen people have with both programmable switches and NICs is they want to throw stuff out. They say, I've got all of these protocols that are supported that I'm not using. So they're sitting there as a liability. If something goes wrong, I actually don't understand in those protocols if one of them gets triggered or tweaked or switched on by mistake. What I'd rather do is compile a program that only contains the features that I'm using.
Devote all the resources to the switch to supporting that.
Exactly.
Tables maximum sized rather than having empty tables for features that are something you're never going to use.
So I want to jump in with a quick point of order. So please do ask questions. And I think for the three of us, I believe that possibly the audience cannot see the question. So we should repeat the question when we answer it.
Okay.
It's only private to us. So I want to go next to a sort of hard question, sort of an elephant in the room. Intel recently announced that it's going to halt the future development of Tofino line of switches. That doesn't mean that Tofinos won't be around for quite some years, but the further roadmap is not going to be developed. So what does that mean for the future of data plane programmability and P4? And Nick,
I should probably take this one, shouldn't I? Barefoot, the startup that designed and created Tofino, started in 2013, just at the same time that P4 started. And that wasn't a complete coincidence. It was at the starting of Barefoot that it really became very clear. If you wanted to be able to program switches at line rate, then you needed language to do that. And we could have chosen a proprietary language and come up with something that would just be targeted at that particular architecture. But we thought the need was greater that it would be much better for the field of networking if we could create a language that would outlast particular switches or FPGAs or wherever it happened to be that the packets were being processed. And so that was why, if you read the original P4 paper, it doesn't talk particularly about Tofino or particular switches at all, or NICs or whatever they happen to be. It was very much targeted at being a more general language. And that was good because it kept us focused on having a language where you specified the behavior that you want with as little knowledge as to how it would be implemented underneath. The first version, P4.14, kind of got a little way towards that. It was probably a little bit too tied to the underlying assumptions of a forwarding pipeline. P4.16 improved and generalized that. And so I think that P4 really got a start with a view to being much more general purpose than a particular switch. And but of course, it's always been a little bit tied to Tofino because Tofino was the first of the P4 programmable line rate devices. And, if I look back, I think there was an element to which it was a bit of a hero experiment, right? Could you actually build a switch? Because switches are much more, higher capacity, leading edge. They're always using the leading process node. They're the biggest chips that you can possibly make. They're always what's called reticle limited, which means they're the largest manufacturable devices you can do because they've got so much I/O on them in order to talk to the outside world. So they're sort of super challenging. So it was like we were trying to say, if you could make a switch programmable, you can make anything programmable at line rate with the same power, performance, and area. And in 2016, when the first Tofino came out, it just so happened it came out in the same month and was available in the same month as the equivalent fixed function device. Happens to be from Broadcom, the Tomahawk 2. They were both available in January of 2016. They were both operating at 6.4 terabits per second. And it turned out that they had the same power, performance, and area. And this is crucial because what it proved was that there was no need for any compromise when building a device that was programmable. And there's a good reason for this. The reason is switching chips are mostly I/O. Well, at least 30% of the area of the chip is I/O. It doesn't matter whether it's programmable or fixed. About another 30 to 40% is the lookup tables and the packet buffer. That doesn't matter whether it's fixed or programmable. It leaves a small portion of it that's the logic that determines whether it's fixed function, those 45 protocols I mentioned earlier, or if it's programmable. And it turns out that the difference between them is very little. So there's no magic here. It was actually a problem waiting to be solved way before we came along to do that. So the simple reason that Tofino then was possible was it was abundantly clear that you could make a programmable device of the same power, performance, and area, and therefore the same cost structure. And so there was no reason for them to be fixed function. It really just remained to be seen. Was there a business to be made there? So there was Tofino 1, there was Tofino 2. There would have been Tofino 3, which would have been a 25 terabit per second switch about now. And as you know, we hit an economic downturn last year. I was in the unfortunate position of having to make a decision between a number of things. It was a purely economic decision. It wasn't that there was a lack of interest. There were quite a lot of customers that were and still are using Tofino 1 and 2. And Intel has said publicly and to those customers that will continue to support the 6 and the 12.8 terabit per second Tofino 1 and 2 until so long as people keep buying them. And we see no plan for an end of life or a stopping of supporting of that for many years to come. And in fact, there are people that have started to build new products and new networks based on them since we made that announcement. It was just simply, we couldn't afford to do the next generation. For those that are interested, it takes about $200 million to develop a chip these days in industry, particularly a chip of this type. And $200 million was in an economic downturn is something that we just couldn't prioritize. So we just had to make that business decision. What it did allow was us to focus the effort where we see the most interest in programmability. And that turns out it's in smartnics, or what Intel calls IPUs. These are devices that have a fast packet processing pipeline programmed in P4 and a set of CPU cores. And they go together to offload the infrastructure. It's public that we co-developed that with Google. There are other ones from NVIDIA and from AMD Pensando that work in similar ways: programmable packet pipeline and a set of CPU cores. And so it turns out that most software developers would prefer to add network programmability closer to the server, right into the NIC, and hence the term smartnic or IPU and DPU that started to be used. But this is where the action is. And there's a business reason for this too. Every server has a NIC. There's only one switch for about 48 to 50 servers. So it's a much bigger business. And so that's why at Intel, we decided to put all of our effort into the Mount Evans and the future Mount Morgan IPUs, and because that's where we see the biggest market. So we think that programmability, network programmability in the form of P4 programmable elements will be alive and well for some time. And we were able to put all of our compiler effort, all our language effort, our applications, both into the smartnics, the ASIC-based and the FPGA ones, as well into the effort that we do for putting P4 into the kernel. So we think that that's where most of the action will be in future.
Yeah, I agree completely with Nick. And just two things to add there. I think if you look at the history of what went on in data center networking, really what goes on in a large data center is the whole network is one big switching fabric. And the network interface cards are the line cards for that one big switch. And so I think if you think about the data center in that way, the vision that Nick just outlined, because you got to change your name. It's confusing to talk about NICs with Nick.
You can refer to me as Dominic. You can refer to me as Dominic. The rest of them are smartnics.
But I think if you think about programming a distributed collection of network interface cards, and they think of the data plane switching network as a fabric, potentially a dumb fabric if it's not programmable or is closed in some way, that you really still have essentially an extremely large, extremely high throughput switch with pipelines that are programmable at all the line cards, which are the NICs and the servers. So I think, to me, that's an exciting opportunity to think about a lot of the research we've been doing in a context where the scale is even larger than what we've been thinking about with the Tofino switches, because the number of NICs in a network is larger than the number of ports in a single switch. The second point, I think, looking back to early sort of prehistory, before any of this programmability or even OpenFlow existed, I think all of us as networking researchers were always struggling when we had a new idea to demonstrate or evaluate it in some reasonable way with an idea that it might later get adopted. A lot of the existing switches that are not Tofino, they don't have an open programmable interface, but they are still more programmable than their configuration interface might suggest. And also, vendors change their products over time. So it's true that the path to deploying a new idea is going to be harder if there aren't programmable switches some years from now commercially available with an open interface. But it doesn't mean our ideas can't be evaluated in a much more realistic way than they ever could have been 10, 15 years ago. And that it's also the case that multiple vendors, even without open interfaces, have a way of adopting our ideas if we're able to vet that they really are useful and can run at line rate under some reasonable assumptions of what modern hardware is capable of doing. And so I still view both P4 and the Tofino switches as a really important way to tie your hand behind your back and make sure that your ideas are implementable at line rate, even if their deployment platform is a different one down the road, whether a NIC or a different vendor switch.
So I'm going to jump in with another dimension to this question. It's from Eric Campbell in the chat. So he references Scott Schenker wrote this CCR piece recently about sort of how we organize SIGCOMM. And the first half of that paper makes a really compelling case that the goal of SIGCOMM should be to lay the intellectual foundation for the future of networking and network systems. And that's that's what our quest should be. So can you comment on, obviously for PhD students who are working, some of them doing a lot of work with Tofinos and P4, how should they think about their research portfolio and path, and how do they chart this kind of daring path where they're laying the intellectual foundation for the field amidst sort of the commercial forces that are always kind of creating frothy waters.
Yeah, I think it's, in some ways, I think that what we've just seen happen with P4 and Tofino 2 is a good example of this. It's obviously one that I'm closer to, and in terms of the original idea behind a programmable switch was, oh my gosh, with what's just happened in SDN, we're taking vertically integrated closed proprietary networking systems, we're opening them up and having interfaces between them. But unless the hardware and the switches are programmable, then really what's going to happen is that we're just going to be held up and ossified by those switches themselves. And we were very fearful that the fixed function nature of switches will kind of keep everything closed. So the original RMT paper that was at SIGCOMM was not about a commercial design. We didn't particularly think that that would be anything commercial, and it was very slow compared to the switches were available at the time. We were just trying to understand, was it possible to build something programmable? And so there was a sort of an intellectual component to it, which was saying, hey, industry, you could actually build something that was programmable, that was really no compromise in performance or power compared to the fixed function devices that you built before. Now, it so happens that we were looking at this and saying, okay, well, let's go and try and do this ourselves and make this happen. But what it led to was several programmable switches with different degrees of programmability. It affected the way that other switches are programmable. It affected the kind of features that people expected in order to be able to change to different degrees and different designs. Hey, that's competition. That's how industry operates. And that's a good thing. So I think that this is one example, but we see this happen all the time where those intellectual ideas. So I think that rather than thinking about SIGCOMM papers as should be following an industry trend, I think it's much more interesting if you can start an industry trend and be able to start people, sort of force them into thinking about new ways of building networks and new features and capabilities. And that's really, I think, the beauty of SIGCOMM.
Yeah, I agree completely. And just to add a little more color there, I think in the particular area of programmability, I think it's there are three things we could be thinking about if you're a student. I think one is the IT infrastructure as a distributed collection of heterogeneous components. I mean, that came up in the earlier question. That includes the radio access network, the switches, the NICs, software components like Intel DPDK or eBPF. And so being able to program the entire distributed IT infrastructure rather than a single component, whether a switch or something else, I think is a really exciting area because most network owners are managing that conglomeration of different kinds of devices. A second is a focus on use cases. You know, is it drones or video or smart agriculture? Or pick your favorite use case and drill down into what its implications are for how the infrastructure should support that use case. That's, I think, a really exciting area too. And then a third, which we've seen a lot of, is what are the intellectual foundations we need if the IT infrastructure is going to be more programmable, whether it's better data structures or better programming languages or better verification or some better optimization techniques, some disciplinary hammer being brought to bear on an infrastructure that's inherently more flexible than the one we had a decade ago. Is there's a huge number of interesting problems that are not tied to any particular vendor product.
That resonates, the model you described, Jen, resonates very strongly with me, and it a little bit takes me back. I think to some extent, the P4 community has been focused on, okay, there's a high degree of parallelism, but the language model is pretty sequential, and that was a deliberate design choice. But it's one device or one pipeline on one device, and again, hiding a bunch of the parallelism and making it sequential. But what drew me into networking early on, and 15 years ago, was the idea that this is a great playground for experimenting with ideas in distributed programming and concurrency and all these really hard problems that programming language people haven't really fully solved. And so it's very exciting to think about this one big switch abstraction with programmability maybe in the NICs or in the end host stacks, and starting to think about what how do we program that beast? Because it's a lot more complicated, and there's questions about coordination and concurrency and all of that. So I think there's a whole bunch of stuff to be done above that, and pretty greenfield still. Let me move. So there's a bunch of questions in the chat, which is great. Maybe I'll go to a couple of questions from Josh and Lynn. Asking first, Nick, you said that sort of smartnics kind of all look the same. They have a P4 pipeline and some CPUs. Do you think that, I mean, is that inevitable that will be the sort of standard architecture? And then a second question, which is maybe a little bit more open-ended, like P4 was designed to not be tailored to a single switching pipeline, but still it was sort of co-designed with, with a Tofino-like device or a PISA-like device. So it's not obvious that P4 would be the right programming language for a totally different kind of device like a smartnic. Any thoughts on that question, and maybe what extensions or evolutions might be coming down the pike?
Yeah, right now we've seen the emergence of the smartnics, IPUs and DPUs over the last few years. Amazon was the first with their Nitro, which they introduced into their data centers a few years ago. And now other hyperscaler cloud data centers are doing the same thing, and we'll see that going through to many data centers over the next few years. What is it that they really want? They want to be able to process packets in programmable ways, in ways that allow them to introduce new behaviors, new telemetry. It's very, very similar to switching. And for that, P4 is perfect. P4 is just the right language that you want for describing and defining that packet processing. It may need enhancements for things like encryption, for compression of data. And I think that we'll see that emerge over time. As people become more concerned about partitioning and scheduling and partitioning the resources of the network, enhancing to traffic scheduling, just like we've been working on for switches. So there's a lot of similarity in the processing pipeline. And so my own expectation is that for high performance NICs, you'll see that packet processing pipeline be similar to the Tofino type of pipeline. There will be competition amongst different vendors. That's good, in which they'll try out different ways and they'll have different capabilities, different features, different power profiles. Hey, that's good. That's good. But having a common language for that packet processing pipeline. Now, as packets are coming in from the wire, they can potentially go off into these CPU cores that are used for either things like microservices that support either infrastructure or in future may actually provide the sort of the vSwitch capability right there on the NIC. How people use those will really depend on what they're trying to do. Probably the code that's running there will be a combination of an operating system, some kind of container system, microservices, etc., that are running there that will be written in conventional languages, of course. Then the question is, how do you exploit this fast packet processing pipeline to offload things that help there, to do processing on there as packets come in? My expectation is that there will be some blend between something like ePPF and DPDK and P4. So you can express it clearly in terms of the behavior that you want, and then be able to compile and run it on that fast packet processing pipeline. So in answer to your second question, which was really about how the language will evolve, I think the language will evolve first to allow those extra features you need for compression and encryption and traffic scheduling, just as we would have done for switches. And then it will evolve to blend more with ePPF and DPDK so that we can bring together code that can run either on a CPU or in a P4 pipeline. There is a fabulous PhD thesis, or maybe even 5 or 10, on exactly how to do this and bring those together. And I think it's a wonderful area of research, which could have a very big impact.
A follow-up question to you, Nick, on that. I mean, around compression and encryption in terms of what can be done at line rate at the kind of speeds these NICs might operate at. I mean, I think that was often a question, because Tofino didn't really support encryption in the data plane. Do you think that was just was actually hard to do at that kind of speed? Or
it just wasn't, it just switches typically don't do compression and encryption and not really cool to do that. It's something you want to do on the end host because it's closer to the root of trust. And for compression, it's closer to the storage, where you want to decompress and then put it into storage or then process it at the endpoint. So actually, all of the smartnics have either fixed or programmable encryption and compression at line rate today. And so it's very doable. Actually, the algorithms lend themselves very well to being put into programmable hardware. So you'll see that continue over time. And
interesting research area to figure out the right sort of programming abstractions for doing encryption or compression? Is that something you feel is solved already?
No, not in a general way. It tends to be tied a little bit to specific algorithms, the sort of the popular algorithms. And so I think there's probably a very nice abstraction down to an instruction set that could enhance P4 in order to be able to exploit particular hardware structures. So there's a sort of a hardware software co-design, I think, or hardware language co-design that could go quite nicely.
let me go a different function. So transport, or more generally, the difference between packets and sockets or sessions or messages, whatever you want to call them. That's a space where there's sort of an impedance mismatch in P4. I would argue P4 is very much designed around packet processing, and you can imagine extending it with either through externs, or like the group that's developing the portable NIC architecture has been making tables more flexible to support certain kinds of flow tracking and so on. But
good point.
Programmable
Yeah.
transport is that's a thing that there's a variety of approaches people want to explore, and it's not totally obvious to me how you would evolve or marry these different programming models to support all those things. I can think of ways to sort of realize it in one design, but to think about a collection of abstractions that somehow nicely cover the space and let you express lots of things and still can be compiled and still kind of fit in with the design of these frameworks. As you say, it's I think a PhD or several PhDs.
Yes. Yeah.
But to me, that's one interesting function that would be a sort of you could sort of look at the design of that particular class of functions.
Yeah, and there's definitely been a trend over the years to TCP offload into the NIC, right? A progression of more and more of the functions of TCP that get put down there. So this seems like a trend that is already happening to some degree, although figuring out how to do it in a way that allows the flexibility at that layer, as opposed to just the speed of offloading, seems like a super exciting. That's another 5 or 10 dissertations. So we got the room for that too.
No, I very much agree. And, in environments where you want super low latency, or you want specific congestion control algorithms that require state being maintained, if you look at the congestion control algorithms that have been published in recent years, most of them would benefit from or already exploit some kind of support down in the NIC. And in some cases, it was one of the limitations of being able to implement it was that they didn't have that flexibility and that programmability. So sort of figuring out good primitives and good abstractions. So I think these are all very natural ways for P4 to evolve over time. And heck, if somebody comes along with an entirely new language for programmable packet processing and forwarding, that's great too, right? It's not as though it's going to be the last word. Languages get replaced over time with ones that are more suitable. There's good research there to be able to say, hey, what if I was to start with everything that we know today with a clean slate? What would I do? And actually come up with a new language. So I think all of these are great research activities to be done.
There are so many good questions in the chat, and I have a long list myself,
Yeah.
so it's going to be hard to choose. But here's one that Stefanos asked about half an hour ago, and I'll rephrase it slightly. So I think the Intel and Tofino ecosystem really did open up the network fabric to be something that all of us could play with. We could sort of complain about we have to sign NDAs and get access to closed software to do that, and you have to work with the compiler. But I would argue still fundamentally it was very, very liberating to have that. It is liberating to have that. But looking forward, do you see more radical versions of open platforms? I mean, even a bunch of the hardware folks are doing open source hardware. Of course, things like RISC-V, but also ways for academics to design chips and get them built pretty cheap. Do you see in some, I don't know, in a decade, the possibility of even more open source network components?
Yes, I do actually. I think that there's a great opportunity for this. I've always been a big believer that the networking hardware should be more open. Many of you have probably found if you go around and talk to different either switch chip vendors or equipment manufacturers, they're all very closed because they just say, hey, we conform to certain standards on the outside, therefore we don't need to tell you what we do on the inside. That's very different from a programmable device like a CPU. You have to say how it works and you have to publish an instruction set, otherwise people can't use it. So there's always been this history and this very public publications of how they work internally, which we've not done in networking. And Tofino was one of the rare ones that did. And even then, there are features inside that probably not published, probably just because of the detail, less because of the intellectual property. So it is a problem that we've always faced. NetFPGA that many of you have used and are familiar with is an attempt to address that. Now, NetFPGA itself could probably do with a refresh and with a combination of Ethernet interfaces and modern FPGAs And FPGAs are a wonderful, wonderful prototyping environment. They accurately reflect many of the limitations that you have in hardware. They're pretty easy to use. You do typically have to sign NDAs for anything that requires a compiler, just because the compiler is a big commercial advantage, whoever's FPGA it is, just like you do with a switching chip. So I don't think that will be rather hard to get by. What we did get past with Tofino is we allow people to publish anything about resource limitation, anything that they were struggling with their papers, and then with their research and fitting and etc., in order to sort of encourage more work. But I think open source designs will be a good thing in the future. Now let's take a look at the specifics though, because it's a little more involved than it seems at first. We actually spend quite a bit of time thinking about with Tofino, should we actually make it open source? Could we make it open source? What would that actually mean? And many of you probably nodding and saying, hey, that would be super cool. Turns out that behind RISC-V was an army of extremely good PhD students at Berkeley that were and other universities totally dedicated all their time to being able to get that going. And remember, a RISC-V CPU is about 1,000th of the size, I think, of a Tofino switch. So it's very, very small in comparison. I don't mean to trivialize it, but because you've got to get all of the software ecosystem around it. And then they had Sci-Fi as a whole company that was then taking that and then commercializing that. So there was a whole army and many, many investors and commercial interest in keeping that alive. And that's really just because of this, you have to have a funded ecosystem in order to keep that going. We don't have that in networking. I wish we did. If anybody has ideas on how to get there, I'm all ears and I'd love to help see that. I just don't know really where to begin. But don't underestimate it. It's a very big undertaking to do it in a way that's useful for people who will be using it.
So maybe I'll turn to Fernando's question. He's asking, it's from a while ago, so we've answered part of it, but thinking about new services that the network might provide in the future. We've talked about crypto a bit, but what about ML? Obviously things like LLMs are in every conversation I have with any computer scientist, so we've ticked that box now, but networks to support ML, there's been some work on this out of Stanford and Purdue, but how do you think about those functions in particular and how they might be realized in future programmable platforms?
Jen, do you want to take that one?
Yeah, I'm puzzling over. I think one challenge for doing this in a PISA-like pipeline is just that implementing, let's say, a neural network, a deep neural network in the pipeline is really challenging. You need a lot of ability to mix data coming in, and there's just not enough parallelism in the pipeline, perhaps, at least the ones that exist today. So probably you're looking at either doing this in an FPGA or an ASIC that's more customized to doing ML, particularly if you want to do training in the data plane. Not sure you even need to do that, but even if you wanted to, it's not clear that the current devices are well suited. The network interface card seems like a natural place, whether it's the network just being in support of doing distributed training and inference more efficiently by helping deal with the unusual communication patterns that might create, or maybe even offloading in a coprocessor sort of way some of the tasks. But it seems like it would be a different kind of hardware device than the kind of things we see in say the Tofino.
It does depend, from what I've seen, the limited attempts along these lines that I've seen, and there have been some publications of methods to accelerate training, particularly in the way that the parameters are shared during the stages of training, depending on whether you're splitting based on the data or on the processing. But essentially, there's typically a process where you're taking a vector or a matrix of values, and then you're changing it in some form or other, and then aggregating through addition, summation, convolution, whatever it is that you happen to be doing during that stage of training. Different methods work in slightly different ways. NICs and switches that have support for this in hardware, just like CPUs that have support for this in hardware, if they've got that support in hardware, they are so much faster, they are so much more power efficient than trying to do it in some serial fashion. So there have been various attempts to have training networks that do this within the network. There are actually some commercial, almost fixed function switches that have some support, particularly for integer operations. but they're not yet at the kind of generality that you would want in order to be able to do many kinds of operation this way. I think it's actually ripe for research, for exploration. My suspicion is that it would be only a relatively small step away from the kind of RMTP and PISA pipeline that we have today and P4. That there are probably things that may just be the narrowness of my own thinking, but I suspect that there's something that's not too far away from that could actually have quite a big impact. So there's a good opportunity for research there, I think.
Great. I want to combine a couple of questions. So I think FR is probably Fabian Ruffy from NYU, and Jun Kim, soon to be of UVA, is asked a question. So many of the academic work that built on Tofino and P4, you'd have some new idea and you describe sort of the data plane algorithm or the broader system. And then there'd be a sort of section 5 or 6 of the paper where you'd say, oh, but I have to fit this into end pipeline stages or so many registers or PHVs and so on. And then there'd be a bit of engineering to make things fit. So the question is, what's the sort of intellectual future of that kind of work? There's also a very interesting line of work, Jen, you've worked on some of this, of thinking about how ideas like approximation or probabilistic data structures can be used to replace, very expensive computations with cheaper ones, or maybe degrading the accuracy somewhat. In the broader context of sort of programmable networks, how do you think about this sort of area and path and its future?
Yeah, the design of the ALU, that which is taking the inputs, doing some twiddling and some function, whether it's a Boolean or an arithmetic expression or something that's focused on machine learning, that ALU, as you might imagine, inside a switch like Tofino, inside any switch, there are thousands of those ALUs. So figuring out what that ALU does is really important. Tofino, they happen to be all the same. You can imagine switches in which they were different depending on the functions that they were doing. Just put it into perspective, a switching chip like a Tofino or the equivalent fixed function devices, they're 400 to 600 square millimeters of die. They're massive. A CPU, which might have one or a handful of ALUs, is a fraction of a millimeter. So it's about 1,000 to 1 difference in terms of between a CPU and a switch. And so those ALUs you can compute are a tiny, tiny fraction of the overall design. This is good. This is good. They're actually not a particularly large portion of the overall area or power. So there's actually a lot of room for improvement. When you're doing a design, you obviously want to make it as simple as possible because you've got so many of them there. It's just less work to design and less power at the end of the day. But they're not particularly limiting. You could really imagine expanding them, whether they're in the NICs or in the switches in future. So having some ideas on what the primitives, what modified sort of new ALU functions would actually be really interesting, I think. There's lots of room for innovation and research there.
Yeah, I'll just add that I think there's still a fundamental mismatch between memory bandwidth and link bandwidth, and it doesn't show any signs of changing. And so I think from that perspective, thinking about data structures that can fit within limited memory is still important. Now, that said, in the network interface card, you might be keeping per flow state anyway, if you're going to be doing the transport protocol, at least partly in the NIC, in which case, trying to do something that is sort of sublinear in the number of connections might not be worthwhile because you're having linear state already. You've already sort of drunk that Kool-Aid. So I think it really depends on the setting. If you're talking about a middle box, deeper in the core of a high-speed network where the number of flows is much larger and it doesn't have to terminate those flows, then I think that's a place where the memory link speed mismatch would argue for compact data structures. And on the end host in the NIC or any BPF, it might be quite reasonable to keep per flow state. So I think the heterogeneity of the devices and the heterogeneity of their locations in the network might drive this decision of whether things that are compact are necessary or useful.
Good point.
So I want to jump to a question from Sundar. For those who were not at the P4 workshop, I guess that's probably most of the attendees. It just wrapped up yesterday. So there was a nice keynote that I haven't actually watched yet, but I heard a summary from my students who were there from Google about how they're using P4 as a hardware abstraction layer. So they're taking switches that they're ultimately not programming in P4, and they're building a description of them in P4, that they then use for validation purposes. And this was their switch V paper from SIGCOMM last year. So the question is sort of, how real is this story? How plausible is it to sort of simply take off-the-shelf commercial switch, fixed function complex, and a bunch of layers of the software that runs on that switch. There's a driver, there's a local CPU, there's a lot of stuff going on, and abstract it as, hey, this thing is just a P4 program. And maybe I'll just sort of pile onto this question. If that was the thing we wanted to do, most with P4 was to use it for this kind of modeling. Like, is P4 the right, exactly the right way, or are there things that we would do differently if our goal was to have a modeling language or an abstraction language?
I think this is a great question and a great topic. Right? Just my own experience observed that Barefoot and Intel has been that it is increasingly common for a customer. They could be building equipment, they could be building a network, they could be a big hyperscaler, they could be someone that's doing something small, like for the video communications industry, something like this. They increasingly will come to us with a specification, and that specification is either written in P4 or it includes P4, and say this is part of the behavior that we want. So rather than saying, I want, IPv4, I want this with this particular header, I want SRv6 or whatever the feature is, they say, this is the behavior I want. This has several benefits. One is it's an unambiguous specification. It actually tells you what you need to build and what you need to provide. And so if they want us to program it for them, it tells us what we need to do. We may in fact take the program they provided and then run that and show them that it compiles. It so clarifies the interface between the customer and the vendor. It means that if you can provide it to them, they've got to do less testing. All they need to do is say, does it work? I've actually got the test program. It's the specification I gave you, and I can do that and run it on several vendors' equipment and see which ones are best, or if I want several in order to have multiple sources. So it is a massive step up and improvement in the clarity of that interaction, the reduction of the cost involved in testing. And you can take this one step further and say that in future, almost any specification like an RFC or an IEEE standard, why not include in that standard and that specification a description that's in P4 or some enhanced version of P4 if that proves insufficient? I think it would be a wonderful contribution to the field of networking if we could make that happen.
Yeah, I was going to make exactly that same point about RFCs. I mean, I think it's ridiculous that we're specifying protocols in ASCII art, right? I mean, it's charmingly retro, but really, I mean, it seems like we really should be trying to do this in a more precise way that's amenable to, something machine readable, something like P4, so that we can actually interrogate these specs to make sure that they're correct and complete and unambiguous, rather than having to parse English and ASCII art to do so. I think the second point, and I think a reason some companies use P4 as an intermediate specification language, is there's this other side of P4, which is P4 runtime, right? They want to have a control plane or a configuration interface that's going to talk to these heterogeneous devices, and being able to leverage a single kind of control channel abstraction for configuring and sending messages back and forth to the data plane is super useful. And even if your device doesn't support P4, it might use P4 runtime to do that. And the spec of P4 is the driver for instantiating that control interface, rather than having to write it from scratch and hope you got it right.
The talk that Sundar was referring to, actually, and that you're referring to too, Nate, was by Praveen Patel at Google. And he was describing how they initially had used a hardware abstraction layer with P4 runtime. That gives them the benefit of describing the behavior that they want and then downloading it through that interface. And so if they want to evolve and expand that in time, over time, they don't necessarily need to bring down the control plane. It allows them to express the sort of the schema for communication in a way that they can continue to enhance, change, modify, or reduce over time. And so this proved, my understanding is that, and as he described it, it proved very well for switches. He was actually talking about how you might do this for network virtualization. Can you extend and enhance that and use P4 as the basis for the how, for the hardware abstraction layer for network virtualization? And it's intriguing. And he gave a very convincing argument that this would be a good way to do it.
So Jim is asking me privately about the keynote. I actually haven't seen it because I couldn't make it out to California this time, but it will be I believe all the keynotes were recorded and will be posted on the P4 website in the coming days or weeks. And I can post it on the Slack channel for the networking channel when that's done. I think we only have time for one more question. These hours always go super fast with you. I'm going to go to one more from the audience. And I'm sorry, I'm probably mispronouncing your name, Egeman. Roughly, you're asking, what's the big next quantum leap, right? So SDN was a quantum leap in introducing, control plane and data plane separation and exploring, things like logical centralization or different units of abstraction for the control plane. And I would argue P4 was a quantum leap by liberating the data plane and saying, hey, this is just another piece of the puzzle that we can program. So what comes next?
I mean, Nick already hinted at the interface to the end host of the network interface card. That's clearly a piece of it, but I'm most excited about the integration with the radio access network in terms of wireless and cellular access networks, and what are the right abstractions for the processing we do there, and particularly integrating that with packet core so that we can really program the network end to end in a kind of single way, as if it were a single access network. And that includes also what telemetry abstractions we might want for 4G, 5G, Wi-Fi, or whatever other radio technologies we have. It's really silly that we in networking think we have an abstraction of the link layer and build on top. But in the wireless domain, that's really not true. The link layer infiltrates all the way into the control plane and into the packet core in ways that really stand in the way of openness and clarity, frankly. And so figuring out the right abstractions for the RAN and what role programmability might play in supporting those abstractions seems super, super exciting.
Yeah, a conversation that the three of us have had with Larry Peterson and with others over the last few years has been very much about how different the world is now compared to how it was 10 or 15 years ago. We can now take it for granted that because of the separation of the control plane and the data plane, network function virtualization, where a lot of functions are moved into software, you can take it for granted that most things between a user process all the way through the NIC, the switches, the kernel, etc., all the way into the other end and the network in between is actually expressed in software by somebody somewhere. Most, not all. And so we're getting towards this point where it's all expressible in software at some level. This is true whether it's wireline networks, and increasingly for the 5G core and for the 5G RAN. The 5G RAN, that's part of what I do at Intel, is helping move that into software as well. And that's very rapidly moving into software at this point. So there comes a point, and I think this is really intriguing to think about. There comes a point in the future where we can take for granted that everything from user space to user space and everything in between, all the way through the network, is specified in software, most of it by the infrastructure owner, but in part also by the application writer as well, end to end and top to bottom because of the control plane down to the data plane and the control plane expressing the behavior at once in the data plane. There is a tipping point in there somewhere, and I passionately believe this. There is a tipping point at which so much of it becomes expressible in software that we will stop thinking of it as a system that's bolted together out of standards. And we will start thinking of it as an entire distributed system. And at that point, networking will just become a subset of distributed systems. And we will think of it as a big programmable infrastructure. That will change everything in networking. And I think that's super exciting. I don't know when that tipping point will be, but I think we should all do everything we can to bring it on as soon as possible.
On that note, I think we need to wrap up and stay on time. Everyone who asked questions, I'm sorry we didn't get to them. If you put them in the Slack, which Matt just posted, I'll do my best to answer some, and maybe Nick and Jen can also as well. Thank you so much, Nick and Jen. It's always a pleasure to talk to you. The time goes way too fast. And thank you everyone for showing up. And with that, Matt, I think you have some station identification for us.
Yep.
Thank you.
So, yeah, thank you very much to Nate and the panelists for putting together such an interesting event. We'll have a recording of this up on YouTube. It's going to be linked off our main website. And we want this conversation to continue. As Nate mentioned, please join the Slack and continue to ask questions of the panelists. The panelists are very happy to continue discussing with you. And Jim wanted to say a word or two about our next event.
Yeah, thanks. Actually, I also wanted to thank all of you for great presentations. Nick, I saw a talk of yours where you predicted the tipping point is happening sometime in the next 8 years. So you don't know exactly when, but I've seen you give an interval of what things will look like in 2030. So I think it's going to be happening. So our next event, so thank you all again. Our next event is actually, it came up in the discussion questions today on AI for networking and networking for AI, sort of the platform piece that was being discussed here. We've got 4 great panelists: Nesh Shroff from Ohio State, Kyung-Young Lee from Seoul National University, Noah Zilberman, who I think might address some of the hardware questions that came up, from Oxford, and Michael Shapira from Hebrew University in Jerusalem. So same time, same place, 2 weeks from now, this is our next event. We hope to see you all there. So thank you all again for really a fabulous session.